Hello guys, welcome on Tesla Adventures. In this video, we'll start the most awaited topic of rigid body dynamics, which is rolling friction. And I would be demonstrating the exact nature of rolling friction in this video and its exact definition. So first of all, the rolling friction is of two types. The one which is the rolling friction on the ideal rigid body, and the other which is the rolling friction on the practical body. Now what do I mean by a practical body? Now when we talk about an ideal rigid body or a practical body, then we can easily differentiate between them by the fact that the ideal rigid body, if we are talking about a round body, so for an ideal rigid round body, the point of contact of that body with the ground, which is also perfectly flat surface, is only one. So when there is an ideal rigid round body rolling on any flat surface, then the point of contact is only single. But this is not the case in the practical scenario, because practically no body is ideally rigid. So when we talk about a practical round body which is rolling on a surface which is also not perfectly rigid, so when it rolls on that surface, then there are more than one contact points of that body with that surface. Therefore, that body deforms that surface which is also not perfectly rigid, and you can see that this object is practical object which is rolling on the surface, and as it will roll, then there are more than one contact points of that body with the surface. So this will deform this surface because it is moving in forward direction, so it would deform this surface, and this surface would create a restoring torque on that body. So this surface would tend to rotate this body in the reverse sense. So this surface would not allow this body to move forward, and it will oppose that body to move forward. So this opposition offered by this deformed surface is known as rolling friction. This distance is known as coefficient of rolling friction or forward length of deformation. But in the syllabus of IIT JEE Olympiads and all engineering or medical exams in India, we are only dealing with the perfect or ideal rigid bodies. So when we talk about the rolling friction acting on an ideal rigid body, we talk about this one. So for an ideal rigid body, which is also a round body, when it is rolling on a flat surface, that surface must also be perfectly rigid, so it is not deforming when the body is rolling on it. So there is only one contact surface of that body with that surface. So this contact surface is at rest at any instant if this body is purely rolling, and we have already discussed that in the case of pure rolling, the velocity of this point B will always be zero. So as we already know that when there is no slipping between any two surfaces, then the friction which acts between them is a static friction. So in this case also, if this body is rolling purely, then the velocity of this point B would be zero, and therefore there is no slipping between this body and this surface, and hence the friction which would be acting at this point on the body would be static nature, and that static friction is also known as rolling friction. So the rolling friction which we will deal about in our curriculum would be the friction acting on an ideal rigid body, and that friction is always static friction. So this friction is not in the syllabus of IIT JEE or any other entrance exam. Now I've mentioned this in this statement that in the curriculum of IIT JEE Advanced, the analysis of only perfectly rigid bodies is included. Hence, the rolling friction which we will deal in this unit would be static friction. So in the case of in this case, I'll demonstrate that in this case, this body, this point has a velocity of v, and this complete rigid body is rotating about its center of mass about with an angular velocity of omega, in such a way such that v is equal to r omega. So this point B has a velocity which is 0, which means that this object is rolling purely and the point of contact is not moving. So we already know that when any object is kept on any rough floor, then there is no friction acting on that object, because that object does not have any tendency to move. When that surface have any tendency to move on that surface, or when that body has any tendency to move on that surface, then static friction would be acting on that body. Because if we are applying some force on that body to slide it on that surface, but that body is not yet started to slide, so there is a friction which is opposing any sliding motion between that body and that surface, and that friction is known as static friction. So in the same case, if this body is already in the state of pure rolling, and therefore the point of contact is not moving, then we can say that there would be no static friction acting on this body, or there will be no rolling friction in this case, which also leads us to a conclusion that if some object which is perfectly rigid and perfectly round, and that object is rolling on any rough surface without any force around it, then that object will keep on rolling forever, because there would be no friction acting on that surface. So now what happens if we tend to apply some force on that body, or we tend to disturb the condition of pure rolling? So in this case, you can see that there is a perfectly round and rigid body which is already rolling on this ground, and its velocity v, and this is omega. So v is equal to r omega. Now we are applying some force which is passing through its center also. So we are applying this force on this body. So this force would tend to increase the velocity of this body v, because we are applying this force. Therefore this force would be increasing the velocity of this body. Now this body was rolling purely, which means that v was equal to r omega. Now you can also see that if v would increase, then to keep this body in the state of pure rolling, omega should also increase. So if this friction would act in the reverse direction, then it would help omega by creating the torque in its same direction, and it would help omega to increase, so that v and r omega are always equal. So if we apply some force F on this body, then to keep this body in the state of pure rolling always, then rolling friction, or we can say that a static friction, would be acting in the backward direction, like that, because it would create some torque which would also increase omega, and this F is increasing v. So v and omega will increase in such a way such that v is always equal to r omega in the course of motion. So now we will discuss different cases in which we'll discuss the direction of rolling friction. Now in the first case, you can see that if v is equal to r omega and the surface is smooth, then this body is rolling purely on this surface, and obviously there is no friction on this surface, because this surface cannot apply any friction on this body. So there is no friction in this case. Now in the second case, if this body is rolling purely on a rough surface, so we have already discussed this case also, that if any body is rolling on a rough surface and it is in the state of pure rolling, then there is no external force acting on the system. then we can say that there is no force which would be hampering or which would be changing the state of its rolling motion. Therefore, there is no requirement of rolling friction to keep this body in the state of pure rolling. It would automatically keep on rolling always. So there would be no friction in this case also, although the surface on which it is rolling is rough surface. Now if this body has a velocity v in such a way such that v is greater than r omega or v is less than r omega, so this surface is again smooth and this body is also sliding on this surface, but this surface cannot apply any friction because it is smooth surface. Now if v is greater than r omega but this surface is rough, so we know that if v is greater than r omega, then this is the condition of forward slipping, because the velocity of this point b would be in the forward direction vb and it would be equal to v minus r omega. So this point is moving in the forward direction relative to the ground, and hence this is the condition of slipping. So to prevent this body from slipping, the friction would be acting in the backward direction. But at this time, as slipping is occurring, therefore this friction would be not static and it would be kinetic friction. And also this is not a rolling friction because no rolling is occurring in this case. So there would be a kinetic friction which would be acting in the reverse direction on this body, and as soon as this body will attain the condition of pure rolling, then this friction would disappear and there would be no friction acting on this body afterwards. Now if v is less than r omega and this is a rough surface, then if v is less than r omega, then this body has a tendency of reverse slipping because its velocity of point B is in the reverse direction. Vb is equal to r omega minus v. Therefore, the friction will act in the forward direction. This is incorrect diagram, don't see it. The friction would act in the forward direction, and this friction would also be kinetic friction, because in this case also pure rolling is not occurring and this body is sliding on this surface. Now if the surface is smooth and v is equal to r omega, then obviously there would be no friction because surface is smooth. And if v is equal to r omega and this is a rough surface, then if we are applying a force at the center of this body, then to keep this body in the state of pure rolling and to keep v always equal to r omega, a static friction would be acting on this body in the reverse direction, so that if F is increasing v, then this static friction would create some torque to increase omega, so that v should always equal to r omega. So you can see that in this case, if we are applying some force that is hampering the condition of pure rolling of this body, then static friction would play its role to keep this body in the state of pure rolling always. So conclusively, we can say that the function of rolling friction is to always continue the pure rolling condition in the body, and this rolling friction is also known as static friction. Now, as we have already discussed that the rolling friction in our syllabus is the static friction, and the static friction always acts when the point of contact is at rest relative to the surface on which the rolling is occurring. So if the rolling is occurring on the ground, then the velocity of this point B would be 0. And if point of contact is not moving at all, then its displacement would also be 0. So we know that the work done is F into S, where F is the force and S is the displacement at which that force is acting. So if we find out the work done by friction in this case, then friction is acting on the body at point B, and this point B is always at rest, and therefore its displacement is 0. So if point B has a zero displacement, then the work done by this friction would be zero, because work done is denoted by the formula F into S, where S is the displacement of the point where force F acts. So this work done would be zero, because the displacement of this point B is zero. But if the body is rolling on any moving surface like that, then the work done by the rolling friction on the complete system would be zero. And the work done by this rolling friction on any body would not be zero, because if you remember, I have already discussed that the velocity of any body is not the velocity of point of contact of any body is not zero. In fact, the velocity of this point lying on this body will be equal to the velocity of this plank. For example, if we write down the velocity of its center is v1 and this is omega, and this plank is moving in the forward direction with the velocity v2, then we can say that v1 minus r omega is equal to v2, which means that the velocity of point of contact on this body is in the forward direction, which is equal to v1 minus r omega, and this velocity is also equal to the velocity of point of contact on this plank, which is equal to v2. So what I mean to say, that if this body is rolling on the ground, then the ground has a zero velocity. So we can also say that the velocity of this point lying on this body would be zero, because v1 minus r omega should be equal to v2, and v2 in the case of ground is zero. So we can say that this point is at rest on the ground. But when this body is rolling on a plank which is moving already, then this point is not at rest. In fact, this point is at rest relative to the plank, but this is not at rest relative to the ground. Therefore, we cannot say that the work done by rolling friction on this rigid body alone will be zero. Or we cannot say that the work done by the rolling friction on this plank alone would be zero. But we can say that the work done by the rolling friction on this complete system, which contains this rigid sphere and this plank, would be zero, because there is no relative slipping between them, and the displacement of this point on the body and on the plank is in the same direction, and it is equal, because this point has the velocity which is equal for this rigid body as well as for this plank. So the displacement of this point on this body and on this plank would be equal. But the friction, rolling friction, which is acting on this rigid body, is, let's suppose it is acting on the body in the forward direction, and then this rolling friction would be acting on the plank in the reverse direction, because friction is a action reaction force which follows Newton's laws. So if friction on this rolling sphere is acting in the forward direction, and friction on this plank is acting in the reverse direction, but the displacement of this point for both of these objects is in the same direction and is equal, then the total work done would be zero, because for this rigid sphere the work done would be F into S with positive sign, and for this plank the work done would be F into S with a negative sign, because for plank the friction and the displacement are in opposite directions, but for this rigid sphere the friction and the displacement of this point are in same direction. So when we will sum up those two work dones, which are equal and opposite in sign, then the work done by friction on this complete system would be zero. So this is the rolling friction, and we'll be now moving forward on the numericals which are based on the rolling frictions.